these experiments, it would be absolutely crucial to know that it comes from dark matter and not from some foreign background. And the directionality is one of the important elements, because the Earth goes annually through the sea of dark matter, and therefore with different velocities. So we will see the signal with a correlation with the season, I hope. And so this is why this is my introduction. Please.
Thank you. First of all, I'm pretty glad to be here, and I would like to thank Professor Zebeda for his very nice hospitality. And second, I apologize for the fact that I have to skip part of this talk in the introductory part, but I'm pretty sure that after a school on cosmic rays, you are being acquainted with a lot of topics which were discussed at the beginning of this talk. And so let me start. This is the name of the people which have been involved in a couple of projects that we have started during last year. So one of these projects is about WIMPs and carbon nanotubes, and the other one is about axions with a different technique that we would like to see can be developed. These projects have been funded by INFM, and in 2016 we will have a proof of concept for those. So, as I said, let me skip some of these introductory slides, and in case I will go to them afterwards. And let me go to the point. So, in the previous talk, we have been hearing about WIMPs. So, WIMPs basically are supposed to interact with matter and to produce some scattering of nuclei because of the interaction. This is not known, not sure that this is really happening. It's not known if this will ever happen, because WIMPs would only have gravitational interaction, and in that case, game over. But if there is some left interaction of WIMPs with nuclei, then there is some possibility that after a collision of a WIMP with a nucleus in a crystal, for example, then the nucleus is extracted from its equilibrium position and moves inside the crystal and releases energy in the crystal, and this energy is detected somehow and registered. Now, this kind of project has been pursued, as I will mention in a few minutes. But first of all, let me remind you a couple of things that are connected to it. So the Earth goes around the Sun, as is known, and this orbit has an angle with respect to the plane of the orbit in the galaxy of about 60 degrees. And the Sun is moving towards the Cygnus constellation with a velocity of 230 kilometers per second. And the Earth is going around the Sun with a velocity of about 30 kilometers per second. And so what happens is that in one season and in the other season there is a composition of velocity or a difference of velocity. So during this part of the orbiting of the Earth around the Sun, the velocity towards the Cygnus is diminished by this vector. In this part of the orbit is increased by that amount. It's a little amount, but there is a variation of the velocity in going towards the Cygnus. So why this is relevant? People think that WIMPs are forming a kind of steady ocean of particles moving at low velocities in the galaxy. So this is a kind of, people think that this is a kind of spherical distribution of particles. The way in which the velocity are distributed is supposed to be the Maxwell way. So they are distributed with a distribution of velocities in which basically use the Maxwell law. And the characteristic velocity in the galaxy is supposed to be about 230 kilometers per second. So on planet Earth, you will have that the velocity of the WIMP, so in the laboratory here, the velocity of the WIMP has to be composed with the velocity of the sun in the direction of the cygnus. And this composition of two velocities gives the velocity in the galaxy, so it's the velocity of the WIMPs. Now, what is interesting is that these nuclear recoils we were discussing before, the fact that the WIMP collides with a nucleus and recoils the nucleus inside the crystal, these nuclear recoils could be sensitive to the motion of the Earth around the Sun. So it can be that during the year you register a different scatter, because during 6 months, say, you will have faster scatterings, and during 6 months you will have slower scatterings. And so this means that there could be a time dependency in the rate of recoils of nuclei in crystals or other kind of detectors. Now, this T here is the kinetic energy of nuclear recoil, and this T here is the time, and the omega is basically the frequency of orbiting of the Earth around the Sun. So if there is some effect which is connected to the fact that the Earth is moving in this wind of wind particles, this is like you are in a car with no glass. So you are moving in a wind of particles which are coming towards you. If there is any effect of this kind, you should see that the nuclear recoil rate has a dependency on time. And this is basically something which has been looked for from the DAMA collaboration in Italy, and probably some of you have already heard about talks by the DAMA collaboration. I know that Paolo Belli was here, so probably you already know these things. There is an interesting plot which I saw for the first time because of Paolo Lipper, who was here. And this interesting plot is about this coefficient here. So it is about this coefficient here, if I can find it. This S of t. S of t is the amplitude of the modulation. It's the amplitude of this part of the process. So if there is a time dependency in the scattering of WIMPs because of the movement of the Earth around the Sun, then that S of t must be different from 0, right? So this S of t has been mentioned by DARPA. And they have an incredibly...
You assume that the WIMPs have some kind of charge?
No. In this case, you assume that WIMPs are neutral and stable, and they have a kind of quantity which allows them to scatter with nuclei. So it's not necessarily electric charge.
Some effective potential that...
Yes, some kind of very weak interaction that makes them scatter nuclei, but this interaction could be spin dependent, spin independent, who knows? There are many, many hypotheses about that.
You assume that these particles are bosons, right?
You can assume that these particles are boson or fermions as well. There are an incredible amount of models around. And I'm not a great expert of all of them for sure, but I'm very agnostic about that. So for us, we assume very basic things. For example, we assume that there is the possibility of having WIMP nuclei interactions, that there is something true in the DAMA results, because that for us is a kind of starting point, it's a kind of conceptual experiment. Let us assume that DAMA has really something to teach us. And so let's see if we can find other ways of looking at WIMP nuclei collisions. That is a kind of starting hypothesis, a working hypothesis. And it's very impressive to me, the fact that they are able to measure this amplitude with an extremely nice accuracy, and the fact that you can also compute curves that fit these points very well. It's something that is really stunning. But to be honest, the largest part of the community, if I understand well, does not believe that they are really measuring the effect that I'm talking about. So this is something to be seen in the future. Indeed, as you can see from this plot that was already shown by Professor Magnan, this situation, these are the DAMA results. So in this plot we have the hypothesis about, it's not working well, this thing, sorry for that. So in that plot you have the WIMP mass, and the cross section. This is the WIMP nucleus cross section. So all these curves are basically telling you, as it was said before, the exclusion limits. For example, if you take a WIMP of 100 GeV and you trust this experiment here, this green curve, okay, then there is no space for cross sections larger than this number, which is about 10 to the minus 47 centimeters squared. So this is the meaning of that. So as you can see, after DAMA is one of the first experiments in the field. After DAMA, a lot of experiments came, and a lot of them were excluding the fact that, for example, DAMA has really seen nucleus WIMP cross-section event with that cross-section. And so if you trust this plot, the situation is really tough, in the sense that all these WIMPs, if you trust this collection of exclusion plot, all these WIMPs are really very much challenged by the experiments today. But if you see this plot more carefully, you understand that, at least in this region, for the super light WIMPs, say WIMPs with a mass less than 5 GeV, the experiments are in a difficult situation. They cannot really say a lot about the exclusion. And you see all these rises here. These rises are connected to experimental sensitivity. The fact that the experiments are not very good at detecting extremely slow recoils. So when you go down with the WIMP mass, you have that, you basically observe a collision of a classic particle moving with very slow velocity, because 130 kilometers per second with respect to the velocity of light is basically zero. So you have a classic collision of a classic particle with a nucleus. And since the mass is very small, the recoils will be very small. For example, for a WIMP with a mass of 10 GeV or so, you are in the ballpark of recoils of 1 keV or so at the velocities which we are talking about. And so if you go down and down with the mass of the WIMP, then the recoils are so mild that the experimental resolution and the experimental techniques are not able to detect them. Anyway, we were kind of trying to understand if we could say something just in the place where all other experiments have defeated this. And this is what we were just looking at, and this is what led us to think about the carbon nanotubes, as I will tell you in a second. So let me just recap the situation. So you are in a lab, you are moving towards the Cygnus constellation, and you imagine that there is a wind that you are experiencing in your lab, just because you are moving in this gas of wind particles. And all of these winds could be responsible for scatterings in the origin of this plot. And then you would have nuclei scattering with this direction n, say here, and this would be the velocity of the initial wind. And so all you have to compute is the probability that a wind with some generic velocity v can make a scattering in some direction. So you have to control these basic kinematic facts. And so this is the starting point. And this holds for all kinds of experiments in this business. So let me skip details and let me go directly to the point. So we thought of a different kind of detector, which is basically based on the concept of carbon nanotubes. So what are carbon nanotubes? It's like carbon nanotubes is like graphene, a graphene sheet which is rolled in a cylinder, right? So this is a two-dimensional surface of graphene, and you have a cylinder which can be 200 microns long and with a radius of 10 nanometers, for example. And this is something that you can produce in labs and you can buy, right? You can buy for not very much money, to be honest. So our idea is the following. Let's do the same kind of experiments that everyone does. The WIMP collides with one of these carbon nanotubes, say, And so it collides with basically one of the carbon nuclei in the lattice of this graphene surface and recoils the carbon nucleus inside the nanotube. Now, depending on the initial conditions of this recoil, many things can happen to the carbon nucleus. For example, if the carbon nucleus, which has been hit by the wind, has an initial direction, which is basically collinear with the axis of the nanotube, as we will see, it has a chance of being driven by the carbon nanotube, which works like an optic fiber and can break around the carbon ion which has been expelled by the surface for the entire length of the tube. And at the end of the tube, you could find a way of detecting it with some technique, which we can talk about. If instead the wind nucleus collision is such that the carbon nucleus is ejected because of the collision with a direction which is not really collinear with the axis of the tube, but is kind of orthogonal to the axis, then this nucleus will hit the other surface. And then if there are other nanotubes around, it will come out from the nanotube and hit another nanotube and another one again, and it will keep on losing energy. And at the end, it will be kind of stuck inside an array of nanotubes, if you can do arrays of nanotubes. And indeed, you can do arrays of nanotubes. These are the arrays of nanotubes that we bought from a company in the US. These photos are pretty recent. And this is something that you can buy for $120. And one of these arrays has a length of, say, 10 millions of nanotubes on one side and 10 millions of nanotubes on the other side. As you can see, they are pretty much ordered cylinders, basically. And you can look at their top. At their top, you can find full arranged molecules which are closing the top, but with chemical techniques, you can cut the tops and open these tubes, right? So what I was talking about before is the following. Imagine that a wind comes here somewhere and interacts somewhere inside this forest of nanotubes. If the initial condition of the ion being ejected by that is such that the ion is parallel to the tube, it will keep on going like that, and then it comes to the top of the array and it can be detected from. Why is this interesting, and why we think that this has something to do with the detection of light waves? The reason is simple. This is the scheme of an hexagon of carbon nuclei. All the electrons are supposed, and are known, not supposed, to be in the surface. The majority of electrons are kind of tightly packed inside the two-dimensional surface of graphene. Only very few of those electrons are coming out from the surface, and they are in these orbitals, p orbitals, and they form a kind of little fog of electrons which has a depth of less than like 1 angstrom on both sides of the nanotube. So what I'm saying here is that if you take a nanotube which is a length of 200 microns and a rate of 10 nanometers, you are considering an object which is basically empty. There are no electrons inside because the electrons are confined to the surface of the nanotube, very close to it. And in the bulk of the nanotubes, there is just nothing. So if you take it in vacuum situation, you have an empty object. That means that if you recoil a nucleus inside of this cylinder, and even if the recoil energy is very small, right, then there will be very little energy loss because the nucleus goes and touches the surface of the nanotube, and as we will see, it can be directed from the nanotube, but it will be meeting very few electrons on its path. And the nucleus electron interaction is responsible for most of energy lost in the other experiments we were discussing before. For example, in the DarkMatter experiment, you have a crystal, which is sodium plus iodine. And in these crystals, you can have channels as well, channels of this kind. But the great difference is that channels in the crystal of DarkMatter are packed with electrons. So if the nucleus is injected in one of those channels, it's going to be interacting with the electrons it meets on its way a lot, and it will be missing a lot of energy. And so if it starts with 1 keV, because the recoil was due to a light wind, it will not make it to exit from the channel and to be detected, because it will stop at some point because of the leaks that it finds along its path, because of the energy loss. The tube offers a possibility of giving a very small energy loss. That's the point. How does it work? It's just classical physics. Because it turns out that people studying the solid-state physics of nanotubes found that if you approach with a positive particle the surface of a tube, then you will be experiencing a kind of repulsing potential, which is due to all the ions making the surface of the nanotube itself. And this repulsive potential can be represented as a barrier with a height of 300, 400 electron volts. It depends on the kind of way you made up your tube. So this is just a very small energetic barrier. So one can think that high energy physics has anything to do with these kind of things. But indeed, you have to look at the transverse motion and at the initial conditions of the ion. So if the ion recoiled by the wind has a transverse energy, which is very small, that means geometrically that its direction is very close to the axis of the nanotube, then that transverse energy can be compared to the height of this barrier. And there could be just an inversion of point, there could be an inversion, classical inversion of point. Just because you have a big drive in the longitudinal direction, say some keVs, and you have a very small energy in the transversal direction because the initial condition were putting the ion really coaxial with the nanotube. And that allows you to be kind of doing a kind of billiard when the ion gets close to the surface. But as I said before, when you go very close to this barrier, then you have to go through this electron fog. But this is a very low density electron fog. So the energy loss that you have when you approach the surface should be really small. And the interior of the tube can be represented like that. This is the transverse plane. These are the potential at the transverse plane. And so you are in a kind of potential of this kind. So you are in a kind of potential, a symmetrical cylindrical potential. So in the transverse direction, you are being reflected. And in the longitudinal direction, you just go. You just go to the end of the nanotube. And many things can happen. There is a lot of things that can be studied here. For example, if the potential has a perfectly cylindrical symmetry, then you can make, then you just conserve the transverse angular momentum. And if the transverse angular momentum is a constant of motion, then, for example, you have a centrifugal barrier at the center of this potential, and that is preventing the trajectories of the ions to go close to the axis of the nanotube. But you can learn things from that. And many other observations can be done, but I don't have too much time for those. And just to say that these potentials can be of different kinds. This is the kind of symmetrical potential I was discussing before, same height at all angles. So you go around the tube and you find the same height of the potential. And these are other kind of potential that you can have, which have windows, kind of windows. These are very much studied in condensed matter physics, and so you can try to bridge the two knowledge, things from condensed matter and from the topics we discussed, to find solutions for these trajectories and so on. It's very fun. As for the detector we have in mind, we think to something like this. You have an array of nanotubes on one side and an array of nanotubes on the other side. And this is a support, just a kind of solid-state support. And then you have you have an apparatus made of an array of nanotubes and another array of nanotubes. You point this apparatus towards the signals, and you can see the directionality in a natural way. For example, if this is the preferential direction of winds coming from the wind, you will have scattering, which allow winds to be directed in the nanotube, and then they exit from the top of the nanotube on this side. If you look at the other side, and the same thing happens here, the wind will recoil a nucleus it will be brought around by the nanotube itself, but at the end it will hit the support and you will not see it. So if you have a way of reading the positive ions exiting from these tubes, you will see an asymmetry because you will read something on one side and zero on the other side. And then you can rotate the detector. You just rotate it completely by 90 degrees or by 180, even better, and you see what happens. And looking at all these correlations, you can find the way of looking at the directional signal. Now, I don't want to go into too much detail, but you see, you can compute a lot of things here. You can compute total rates as a function of the wing mass, and assuming some wing proton cross-section, which is kind of coming from the gamma experience, from gamma data, just to have a starting point to look at some distributions. So you can see the distribution as a function of recoil energy, as in this case. You can look at the distributions as a function of the wing mass. And as you can see from this plot, the wing mass, the light wings are much better for this kind of materials, as it was clear, because you see, the carbon has an atomic number of 12, so as a mass number of 12, and so it is clear that it's preferring light particles. Maximum transfer energy happens at the same mass, right? It's like in classical conditions. And then you can study the anisotropic response. This is the effect that I was discussing before. This is the effect at an angle of pi and at an angle of 0. These are the two phases of the detector I was discussing before. But most importantly, this is the sensitivity plot. This is the things that this is how this kind of detector could be sensible to wings of different mass. So these are wings of different mass. These are the cross sections. And as you see, the sensitivity is very good at low masses, and it decreases rapidly at higher masses. So if you want to put this plot here, in the plot that Professor Mariani was showing before, you are kind of looking at this region with carbon nanotubes. You are going in a place where other people can go. And again, the message is that you might be able to do that just because you have very little energy loss inside the tube, because the tube are empty things, not like crystals. Now, you can do simulations of different kinds that we did, and sorry for that. I had a lot of slides, but then I realized that the time is not much. So, and let me say something about this is a kind of game in mathematical physics, which we are trying to learn these days. So we are looking at these arrays of nanotubes as a Sinai billiard. Sinai billiard is a very much studied system in mathematical physics. So these are the nanotubes from the above, looking from this is just a section of the nanotube, say. So there are many of them. Now, these potentials I was discussing before are potentials that are kind of rescattering you inside the nanotubes, are active also outside the nanotubes. These are symmetrical potentials. So if a particle moves towards the nanotube, a positive particle moves towards the nanotube, it's reflected inside. If the energy, the transverse energy is slow, is small. But if you look at things from the outside, it is the same. Because if a particle approaches a nanotube, and the transverse energy is sufficiently small, it is reflected as well, because there is as well a potential value. Now, forget about the interior of the nanotubes and look at the array. If you look at the array and you imagine that the nanotubes are kind of dense inside, that you cannot enter, it's just a classical obstacle, then you will have trajectories of this kind. And trajectories of this kind happen to be studied for strange reasons by mathematicians in probability theory. And you can compute analytically quantities of the kind of this, which is the time that a particle spends inside a system of billiards of this kind, like 4, the time that the particle spends in this colored region. So if you enter this system, you start going and being scattered, reflected by the surfaces. And this time can be analytically computed, and it's related to the distance between this axis here, and it's related to the radius of the nanotubes as well. Now we say the nanotubes, but mathematicians talk about general things. So why this time should be relevant to us? This time is very relevant to us because imagine that one of these wings collides with a nucleus and injects the nucleus inside the array. So look at the nucleus which is scattered by the nanotubes. Now, there are two motions, as I said. There is a transverse motion and there is a longitudinal motion. Now, the transverse motion inside the array has a time because it takes some time to the particle to reach the perimeter of this array of nanotubes. If the time which is needed to reach the perimeter is shorter than the time which is needed to reach the end of the tubes, because you see there is a drive in the longitudinal direction and there is a drive in the transverse direction. So if the time that it takes for the nucleus to reach the perimeter is smaller than the time it takes to get to the top, then you are losing that ion. You will never see it. So you really want that the time, the transversal time, is long enough to allow these particles to be brought around inside the array and be detected at the top. You don't want to detect them from a precise position. You want to detect them from the top. So we were studying these things with Monte Carlo techniques, and yet we learned a lot of things about this system. Basically, we brought down Monte Carlo simulations tuned on the analytical formulas coming from probability theory. And so we are sure that our simulations are at least reproducing the analytical result in simple conditions. And then we look at more complicated things, like the ion which can enter inside the tube, scattered inside the tube and exit and all that. And at the end of the day, we could find a way of understanding how large these arrays must be. For example, this is the percentage of particles that you are losing from the perimeter. And this is the length of the side of the array of nanotubes. And this is instead, the various colors are relative to how long the nanotubes are. So just consider one length, for example, 100 microns. And then you look at what happens. So if you increase the size of this array above a certain value, you can stay like below the 5%. Like with 10,000, just 10,000 nanotubes on the side, you have a loss from the perimeter which is less than 5%. So you really need small arrays to trap well your ions inside. And this is what the mathematical simulation says. Now, the practical world is another story. We should go to the experimental side and check all these things in a lab and see what happens. Because the physics of nanotubes is not so well known. It's very new. It's just 10 years old field, so you don't find many information. This is just computation and Monte Carlo, which is the easy part of the game. So this is just to say that we were going around and looking at many distributions and looking at fraction of escaping. So you can study a lot of things about these systems. It's just a world of possibility. And then what we will do is to look in the near future and see in the lab what happens. Now, if I have a few minutes, I can tell something else about our last project. Otherwise, I close it here because I'm not sure that I have time for that. So you tell me. I can go. Yes. If you are not bored enough, otherwise, if I'm allowed, I can go for 5 minutes more. Otherwise, I quit here. Okay, seems yes. So we are trying also with other people, people from Scuola Normale di Pisa, which is a non-institution. So we are trying another approach to that matter, which is the approach of looking for axions. Now, actually, these are not the axions of Petrie and Queen. We are talking here about those particles called axion-like particles, which are kind of cheap for axions. The only thing that you assume is that their interaction is of this kind. You have, this is the axion field, and you assume that there is an interaction of the axion field with light, and this is the field of light, and this interaction with light is possible whenever light or axions are going through an external magnetic field, which is H. So this is called the Primakov conversion of light into axion and axion into light. We have to assume that a Lagrangian of this kind, a Lagrangian interaction of this kind exists. This interaction is motivated by the old axion picture of the chain Queen. It is motivated by the things. We just assume something like that. Now, the typical light shining to wall experiments are of this kind. This kind. You have a light source, which is a laser, basically, and this laser is going through a magnetic field. And because of this interaction, there is a chance that one of these photons is converted into axion, and then the axion goes through the wall because it has a very small interaction probability, which is due to this G parameter. So it goes freely through the wall. And then there is, beyond the wall, another magnetic field of the same kind as the first one, which is responsible for the inverse conversion. So the action is converted back into a photon. What is really nice about this experiment is the fact that the energy is conserved. Energy is conserved here and is conserved here. And the tree momentum, of course, cannot be conserved because the photon is a massless particle and the axion is supposed to have a very small mass. So there is an exchange of tree momentum and a perfect conservation of energy. And that, this is working really bad. That perfect conservation of energy, oh my God, is giving you a very interesting effect. So if you know your light source, if this is a monochromatic light source, you will see here the regeneration of a photon of exactly the same energy or frequency of the photon which was produced in the laser. So you know the source, you should see there photons of the same energy beyond the wall. Now these experiments are already being done. There is a facility at DAISY which is doing this. It's called ALPS. It's a fantastic experiment. They didn't find anything, otherwise you would have heard about it. There are projects of doing ALPS 2, which is an extension of ALPS in the future. There is another experiment at CERN of the same kind, which is called CASTRO. And it's the same philosophy, but you have only one magnetic field. You are looking at the sun with one magnetic field. And if axions are produced in the sun with this Primakov effect, then you should see photons produced by the axions coming from the sun. So axions coming from the sun go into your magnetic field at CERN, and you still should see light produced out of the dark. Again, also CAST put very important bounds on axion-like particles. And the probability of conversion, this is the probability of conversion, this is the rate of photons produced by source. So this is the rate of photons produced by source, this is the probability that a photon goes into axion and back. As you can see, that probability is proportional to three things, basically. The coupling, which is a very small thing, very small number, with present exclusion limits, so that is dumping you that product immediately. The strength of the magnetic field to the fourth power, so if you have good magnetic field, you can do better. And the length of the path inside the magnetic field. So if you have a magnetic field for a big extension, you can do better. So the idea we were proposing here is that just to change the kind of source. Not using lasers anymore, but going into another kind of source, which is microwaves. You can say, okay, microwaves is, again, a light source. And the point is that no one has tried to use microwaves up to now, because there was very little known about the technology of detecting photons, single photons, in the microwave range. So I suppose that you can build a detector at 30 gigahertz for single photons. And in that case, you could use microwave sources that are immensely more powerful than lasers. These are called gyrotrons. Gyrotrons are producing 10 orders of magnitude more photons per second with respect to any laser source, the most powerful laser source. And you can have continuous wave for gyrotrons. So if you are able to develop detectors of that kind, you can do a big jump in this business here. These are gyrotrons. You can buy them. They are just something that can be bought and ready to use. The only thing that you cannot buy is for sure the detector. So we have in PISA a group of people which promises to be able to go down to the single photon efficiency for 30 gigahertz photons, which is a very nice effort. And 30 gigahertz is not a magic number. 30 gigahertz is because if you go down to 1 gigahertz, then you start catching all the mobile phones everywhere. So mobile phones are very, you have to avoid that. So you have to be you have not to go too low because of that, and you have not to go too up because you don't want to lose the number of photons you can. So you have a megawatt source like the gyrotron. If you decrease the frequency, you lose. Sorry. If you increase the frequency, you lose in terms of number of photons that you can produce. Anyway, just to go to the end, this is well, I had very much. This is our last conclusion. So with microwaves, you can do much better than the experiment that they see, for sure, if you can detect single photons. And you can do even better than CAST. And remember that CAST cannot be really compared to ALPS kind of experiment because you don't have a model, you don't have a reliable model for the axion production in the sun. So it is different to have a source that you control and a detector that you control with respect to the sun, and the detector. So you really have to compare our solution with them. The only problem that I could discuss, but I finish here, is that we go again down with the axion mass. So we are sensible to axion masses below a certain limit. So we go from here down to whatever axion line particle masses we want. So this is just to say that maybe maybe my little learning about it's just 1 year that I'm trying to distill. So what we learned is probably that probably it's not really needed to write down the n+1 model in DarkMatter or the n+1 theory, or that there is a lot of stuff around and very interesting possibilities. What is impressive is that on the experimental side, people use always the same technologies, always the same approach, always the same all things, and much more can be done on the cross borders between theory and experiment. So if you look at experiment, you try to use your ability to compute or to do Monte Carlos and things like that, probably you can be kind of more useful to maybe to the DarkMatter community than just being on the side of theory only, or just being stuck in with the same kind of experiment that people is doing. For example, for directionality, everyone is using gases and crystals and stuff. So if you propose something different like this, people immediately look at you as a strange beast. But then it's funny because you can find a lot of new possibilities. So that was my experience. So thank you very much for your patience, and I finish here.
Bueno, sí quisiéramos ver a los jóvenes que intervengan también con sus preguntas. Estoy seguro de que no todos los conceptos que aquí se mencionaron están claros para todos. Muchas cosas son nuevas y sí sería muy provechoso para todos tener las inquietudes y preguntas de los estudiantes que están ocupando la mayor parte de las dos últimas filas. Es algo en español para que se motive. ¿Sí? Yes.
How can you prevent non-dark matter particles of trimming your nanotubes?
Of course, yeah, this is of course something to be done immediately. So this means estimating the background. So you should go there, take your array of nanotubes, and then you have to put that on a beam and try first of all to understand how it behaves when you expose it to a beam. Beam means, for example, electrons. Electrons can scatter nuclei and not the ions. I'm just talking about low energy scattering. And so you can start counting, and then you have to compare with other sources of background, for example, neutrons. There are a lot of neutrons around in labs, so neutrons can immediately switch on this kind of interaction. So you have to estimate all these things. And for sure, the backgrounds you are talking about are very tough backgrounds, but they are not directional. That's the point. So the way with which you fight with the background in a kind of experiment like this is to exploit directionality. The signal is directional, and the background, to be a real background, has to be directional as well. But the standard backgrounds that you have are not producing that beautiful theta equal to 0, theta equal to pi effect. At least, okay, they also can, but the background is very much reduced. So all these things should be put at work. So we have just a little ad. So we probably will have some support from INFN for the next year. Sorry, that is for sure. We will have a support from INFN for the next year for the proof of concept of experience. So if any one of you is interested in giving an hand, we can discuss. In the sense that we have 1 year time to look at these things practically, and we have a group of people. Unfortunately, some of them took position abroad, like one is at UCLA with Germini, and you know, but it will be interesting to talk about this possibility and doing things like you asked about estimating the background is a big issue.
Bien, ¿alguna otra pregunta? Si no hace pregunta, no va a haber comida.
Comida, puede cubrir. Okay, so it's better. Yeah, there's some.
So I'm not young and I'm not sitting in the Bible group. So I like your talk a lot, and I agree with your last statement about, you know, moving from the WIP paradigm towards these kind of things. I think is a great idea. But I do have a question, just a curiosity. Do you know why the efficiency for the nanotube setup goes down as the height of the nanotube increases?
No, the point is that if the nanotube is too long, even accounting the models of energy loss on the electrons that you have inside the nanotubes, and that you can just import from solid state community. Then if the tube gets too long, even if those electrons are few and all that, you will be losing energy a lot. Because to get out from a long tube means that you have to make many scatterings on the surface. And each scattering is subtracting new energy. So you want to be sensible to the very low energy side. And if you go to that situation, you will, at some point, you will lose. Because at some point, that will, you know, when the ion stops its longitudinal motion inside the tube, it is supposed to be catched by the surface. It kind of stuck somewhere there. So first of all, you have to heat up the system in such a way that you emit all the oxygen, fixes a lot on carbon. So you heat it up like 500 kelvins, then you remove all these impurities from the tube, they are empty, and then after that, you have to find the optimal length of the tube in order not to lose much stuff inside. That's how I understand it.
¿Alguna otra pregunta?
Sí.
Yo tengo una gran duda. Según lo que vemos, la mayor parte del universo está compuesta de energía oscura, y después de materia oscura. Pero nos han hablado de que la mayoría de centros de investigación que se dedican a los rayos cósmicos también investigan materia oscura, pero no nos han mencionado nada de energía oscura. Entonces mi duda es que si también hay centros de investigación que se dedican a explicar la energía oscura.
You see, maybe I got your question without translation. I don't have a very deep understanding of the dark energy business, but what I can tell you is that all particle physicists are much more at their home when talking about dark matter, because if dark matter is made up of particles, then you can use the bulk of the knowledge of particle physics to detect it, to discuss it, and to give it a connotation, like thinking that dark matter is the supersymmetric light particle. Dark energy is a kind of different field. You cannot say that dark energy is made up of particles. I wouldn't say that. It's something that you feel like comfortable with, at least. This is my case, and my understanding is reduced. So I'm sure that Paolo Liberi has something to say.
Well, I think, sí, yo creo que los biólogos científicos reconocen muy bien que el problema de la energía oscura es muy importante. Es muy difícil, ¿no? Yo creo que lo que se está intentando de hacer, y hay esfuerzos muy grandes, es de estudiar su evolución cosmológica. Entonces se hacen estudios para ver cómo el universo si esta forma es constante o no es constante. El problema es que la diferencia es que la dark matter tiene estructuras que son diferentes lugares, que se pueden entender su naturaleza. La dark energy es algo que es homogénea en todo el universo. Y entonces el programa es reconocido como fundamental, pero digamos, yo creo que la gente invitaría al profesor Miami, no se entiende cómo hacer eso, tal vez no sé, yo creo que es un problema que tal vez para ustedes es el problema que van a enfrentar, porque es una dificultad muy grande. Yo creo que hay una dirección de estudios en que se están invirtiendo mucho, porque si la dark energy es constante en la historia de la cosmología, no es constante. El problema de su naturaleza es mucho más difícil, porque es muy difícil. Yo creo que tal vez, como se dice, hacer experimentos que para comprender su naturaleza son muy difíciles para imaginarse.
Bueno, yo creo que están haciendo ahora preguntas muy difíciles.
Pero quisiera comentar, la pregunta de él fue si existen algunos, y la verdad es que no, o sea, no hay un experimento.
Sí, sí hay experimentos, sí hay esta voz, esta voz que no recuerdo su nombre, de seguir, que están haciendo un survey, tratando de ver exactamente cómo está expandiéndose realmente el universo. Y hay participantes mexicanos en esos experimentos.
¿Qué experimento mencionas, perdón?
Está Bessie y vos, por lo menos, que los dos están dedicados a hacer búsqueda, una búsqueda, surveys, mapas de energía oscura, de cómo está expandiéndose realmente el universo.
Ah, sí, o sea, experimentos.
Pero esos son experimentos que permiten acotar el porcentaje de energía. Claro, pero no hay ninguna idea de búsqueda de qué es esta energía oscura. Eso no lo sabemos.
Porque esos modelos.
Sí, bueno,
Esos modelos, y esto está tratando de hacer observaciones, donde, como dije, hay colaboraciones mexicanas, para ver cuáles modelos pudieran explicar, pero como no estamos viendo, lo único que vemos es aceleración, no podemos hacer mucho más. Pero sí lo
Sí, pero yo creo que hay un equívoco en la figura que pone junto a la materia oscura con la energía. El equívoco es que parece que las dos cosas son lo mismo. No son, porque la materia oscura es liberada attraverso su gravitación, una fuerza gravitacional, y es normal de asociar eso a partículas. No sabemos que la gravitación es asociada a la energía de la partícula. L'altra cosa, l'interpretazione más simple es que es una constante cosmológica. La constante cosmológica, el misterio es por qué tiene este valor. No es algo que se misura misurando scattering, etc. ¿Por qué la constante cosmológica tiene este valor que es completamente no convencional? Y se pensaba en efecto que el valor era natural, era cero. Y ahora se descubre que tiene este valor, que es un valor pequeñísimo sobre la escala de las partículas elementales. Eso es el misterio, pero el gráfico que yo enseñé puede dar equívoco, porque se piensa que hay materia y energía y no sabemos que la materia y la energía se pueden intercambiar. Allora, ¿por qué yo hago una misura de la materia oscura y no de la cosa? Son dos cosas diferentes. La dark energy es la manera mejor de visualizar, es una constante cosmológica, es una constante de la cosa. No sabemos por qué tiene este valor.
Disculpe, el efecto Casimir,
¿Sabes?
tal vez el efecto Casimir, la posibilidad de conocer, digamos, tú dices que el valor natural es cero. El valor natural tal vez es
cero o
inclinado to the fourth o algo así. Hay idea de estudiar que tal vez se puede conocer la energía del vacío. Al final, la dark energy es la energía del vacío y en principio se puede estudiar en un laboratorio, ¿no?
Sí, la energía del vacío es exactamente. Para estudiar eso necesita una real teoría de la quantum gravity que no tenemos. Allora, yo puedo decir que la energía del vacío es una constante natural que es como la constante de estructura fina. En efecto, la constante cosmológica es una constante natural. El problema es qué relación tiene con las otras energías del vacío que no conocemos, de donde existe el efecto Casimir. Nos pensamos que hay contribuciones a la energía del vacío que llegan de virtual particles de varios tipos, pero todas esas tienen dimensiones que son completamente inconmensurables con el valor de la constante. Allora, eso es el misterio. No voy a decir que no hay un misterio, pero es un misterio diferente que el misterio de la materia oscura. No es tan ingenuo de considerar las cosas un misterio cada vez. Ahora el misterio de la materia oscura y después pensaremos después.
Bueno, estuvo muy buena la pregunta, evidentemente. Así que vamos a ver.
Y pensaremos después de la comida.
La mayoría de ustedes ya saben dónde se come. Los que llegaron hoy, seguiremos a los que sí saben dónde. Este es el edificio que sigue.
No, carissimo, mi aspettavo qualche tua osservazione.
Ah, su questo punto la
Really nice.
ya no se hacen.
No, because that's already being done, so we're looking for something another. It's just the expectation. So the laser into a vertical system so that you are sure everything is really we do bring that up, and then we wait for the actual to bring that to the ceiling. And then the expectation, things like that. We're studying to see if it's potentially technically well, my focus, I'm not here but I'm just supporting the but it's very, very interesting.
And that is it, it's vision.
Exactly. And these are technical experiments with, it's going to be amazing.
Okay, I will. If you have something,
We're planning to have a meeting. We're still not planning. I'm trying to have it on February. Yes, in Mexico, somewhere in Mexico. And I'll let you know. Yes.
We have been fighting for 1 year. And then at the end, your things happen.
It'll start. Yes.
I don't know.
It's an experience.
If you're not a computer, you look at things on the computer, the real world.
We'll see. Let's just go ahead.
Yes,
Lo que pasa es que todas las partículas se están dividiendo en velocidad, pero todas las partículas están perdiendo energía. Entonces suben el mismo pedazo de energía. Entonces la energía al interior de este pedazo de universo es más pequeña. En ese sentido, la energía no se conserva. No, claro, la energía se conserva en el sentido que ese pedazo de universo sono sempre un punto di tecnologia che la sua cada partícula tiene
el edificio que está
transformando entonces hay una forma
subiendo las escaleras.
escribe la ecuación de
¿La cafetería?
No,
de estos edificios.
Cuando el gas en expansión, el gas la energía cambia, pero la energía se tiene el trabajo en el exterior. ¿A dónde está el exterior? No está
Sí, porque
cuando se expande a la energía no solamente de los